Let's now switch to a new topic entirely, the topic of power. This is how we begin to understand actually the flow of energy through circuits. So as an illustrative example here of this concept, let's imagine I have the following circuit. I'm going to have a battery. In this case, we'll treat it as an ideal EMF, an ideal battery with its plus and its minus. And now what I want to do is I want to use it to power two light bulbs. So in my circuit, I'm going to have two light bulbs. The symbol for a light bulb looks like a circle here with a little filament in it. You can think of that as an LED or an incandescent bulb, if you like. And then I'm going to have a second bulb here. Again, the symbol for that is going to be a little circle here with some kind of a filament inside. And then I will complete my circuit. And we can think of these two bulbs here. I'll put a little dashes here to indicate that they're lit up. Once I've plugged them in here with my battery, each of these will have its own associated resistance. So I will call this one R1 and this bulb here R2 because they are going to resist the flow of electricity. It's going to take energy to force the electricity through those in order to generate the light which is going to be coming out. And we already know now, if you were to analyze this circuit, you should all be able to tell me very quickly how much current would be flowing through this. After all, this just looks like my standard battery and resistor circuit, right? So I know then that the current flowing through I will be the EMF of the battery divided by the resistance. And in this case, the resistance is just a simple series combination, so I can add the two different resistances. So it's a more or less straightforward manner for us now to solve for what the current I flowing through the circuit would be. What I want to begin to do, though, is to think about this now in terms of energy. After all, we have light coming out of this system. We know that energy must be coming from somewhere. And ultimately, of course, that energy is coming from the chemical reactions which are occurring in the battery. So what I'd like to do is to try to consider now how much energy is actually involved in that battery. So let's think about energy in batteries. So if I think about that topic, right, so I have energy, right, in a battery. What this battery does in any given amount of time, so in a time delta t, right, what we do is a certain amount of charge, delta Q we will call it, right, which is then equal to the current flowing, because current is charge per time, times my time interval. That charge in that time interval delta t, right, gets moved, pumped from the bottom of the battery to the top of the battery by that chemical reaction. And it's moved, right, through a voltage V. And now let me label some terminals here. So let's call this point A, and up here is point B, right? In a given time delta t, that amount of charge is pumped. The battery takes it from A, pumps it through the battery up to B. And we can think about how much work then is done by the chemical reaction, right? With a chemical work is done, chemical work of, so this is the work now done by the chemical reaction. This is very much like the work that of us, right? Except it's not us, it's the chemical reaction. But the accounting, you can think of the chemicals as us putting energy here into the system. That's the work that is being done when I take charges from point A to point B, and the amount of charge I'm moving here is this charge delta Q. That's how much energy the battery has done, how much work the battery has put into this system. And we know from our fundamental definitions of voltage that to find the work it takes to move a charge between 2 points, that amount of work is simply proportional to the charge, so that's going to equal delta Q. And the proportionality constant is precisely the definition of the voltage. So that's times the voltage going from A to B, like so. Now, the nice thing about the battery is we know what these two quantities are. Delta Q is something here that we've already solved for, so we can substitute in for that. The voltage across the battery from point A to point B, that is something that we've discussed before. It's guaranteed by the chemical reaction to have the value associated with the energy of that reaction. That's the voltage listed on the side of the battery, or the EMF. That would be equal to curly E. So putting this all together then, the total work that occurs, that is done by this battery in time interval delta t, substituting everything in, then is the EMF of the battery, E, right, times delta Q, and delta Q is I times delta T. Excellent. So you'll notice that the work that is done by this chemical reaction has come out to be positive, because actual work is being done. Energy is being put into this system on this side of the circuit. And you'll also know that the amount of energy put in is constantly increasing with time. Every second that we leave those bulbs on, additional energy is required. So it helps then to think about actually not the energy per se, but the rate at which we are putting energy into the system. And rate of energy, as you should recall from your mechanics class, is precisely the concept of power. So when we think about power, and I will write it as a capital P, and the way I write my capital P's is I write a P, but to make clear that it's a capital, I put a little bar on the bottom of it, like a capital print letter P. That is defined to be the power we're putting into the system, is defined to be the work that's done by the chemical reaction in this case. Power is always work per unit time, so I have to divide by my time interval. In this case, that's going to turn out to be very precisely this quantity divided by delta t, so the delta t's cancel, and what I'm left with then is E, the EMF of the battery, times I. That is a famous formula. That's the power that's put into a battery. Here I'll write it like this to formalize it. That's the power associated with a battery. It's its EMF times the current going through the battery. Very good. Now, it helps when we think about a relation like this to, let's run through the dimensions, the units that go along with a power equation like this. Will recall that the EMF of the battery is a voltage, and the units of voltage are always measured in joules per coulomb. Work done per charge moved. The units on current then are how much charge is transferred in a given amount of time. So that has dimensions of coulombs per second. So when we run these things through together, you'll notice the coulombs are going to cancel, and we're left with units for power of joules per second, which is actually the definition of a watt. So that would be power in watts. Now, I'm interested in the work that is occurring as charges are moving from C to D. So let's compute that work. So the work in my given interval of time, again, as the charges are going from C to D, the amount of work in that time is the work it takes to move my same amount of charge, delta Q, between those 2 points. And we know from our general results on work and voltage that this is just the amount of charge moved, delta Q, times the voltage between the corresponding points, the voltage going from C to D. And here now we know a few things already when we come back here to our diagram, right? We know already from our previous analysis that delta Q is just the current flowing, I, because it's the same current flowing through my whole circuit. The current that flows through the battery comes back down through this bulb, and my time interval was delta T. The voltage now, as I go from C, here, let's bring this down just a little bit. As I go from C to D, that is the voltage through this light bulb, or we can think of it as offering some kind of resistance R. But notice this is the downstream voltage. I'm going from the upstream side, which I'll label plus, down to the downstream side, which I will label minus, right? So that is actually going to be a negative number in general, because again, I'm going from a plus to a minus. That's a loss of energy. So I can account for this by thinking about the upstream voltage that we usually have for a resistor, but remembering that I'm going in the opposite direction. So this is going to be minus V up, where up means the positive upstream voltage for a resistor, or in fact this could be for any element. I'm giving you a quite general analysis, but in the case of a resistor, we happen to know in this particular case it's going to be I times R1. But let's just try to keep our considerations general now. Just some circuit element that our current is flowing through. Any circuit element is going to have an upstream part, right? An upstream voltage, and in the direction we're going with the current, we're going to have the opposite voltage from that. Very good. Now, to continue down along with our analysis, as we go through this now, I can substitute in, and I find that what I'm looking at then is going to equal negative. When I substitute in V up, I'll have minus V up times my results for delta Q are the current I times the time interval delta T. And now I think we're ready to put this into some kind of a power equation. Notice that now the power that we are computing, this is actually power that is coming out of the system, right? We are not investing work in the system. That's why we're getting a negative sign here. We are putting negative work into the system. That's the same thing in energy accounting as saying the system is putting out work for us, not us work into the system. The work that we're getting out, of course, is the light that we see for that light bulb. So the formula we're getting here has a minus sign in it, but really what it's accounting for us is the positive power out that is coming out of this particular system. And that power out then is going to be minus of the work that's being done per unit time delta T. And when I take my formula for the work, I account for the minus sign, right? I want the minus of this work. In would then be the work out. And the work out is VI times delta T. So when I divide by delta T, I just have that it's the upstream voltage of whatever circuit element I'm looking at times the current I. And that's a general result then for any element. So the preceding result was special for a battery. This is any element. And of course, I wanted to specialize this thing now for a resistor. So if for a resistor, I actually have a number of forms I can use for this. So the power that is coming out of the circuit due to a resistor, I can write it in this simple form here as I already have it, V up times I. Or I can use the fact actually that V equals IR, right? So I can substitute here in for V the fact that V equals IR for a resistor. And what I will get then is IR times I will get two factors of I squared times R. That's if I use this equation. I can actually run things in the other direction. I could substitute, instead of in for V, I can substitute in for I. I could solve V equals IR and then use instead that I equals V over R. And if I take that result for I and substitute in for I, I'll get two V's on top and then divide by R. So then I would have V squared divided by R. You'll notice when I wrote this equation, I'm not worrying now whether it's V up or V down. The point is it's V squared, so either way, it's going to give me a positive number. I will get the correct formula. So for resistor, we actually have three different valid formulas here for energy. Which one you would use depends on your circumstances. It depends on what you know. If you happen to know the currents, then I would prefer this form. If I already know the voltages, I would use the lower form. And if I happen to know both, sometimes you could use this form as well, though you usually end up knowing either just the current or the voltage, so that one or the other of these turns out to be the most convenient. Very good. So these are our general results then and considerations for energy. Let's see how we're doing in our particular circuit. Are we actually conserving energy for that battery and light bulb system? So let's check that. So let's energy conservation. Check. Okay, so if energy is conserved, we're asking, is the power that we are putting into our system actually equal, and I'll put a question mark here, we want to see if it's going to work, the power that's coming out of our system. Now, the power into our system is the power coming from the battery, and as we already said, that is just the EMF of the battery times the current, right? It's the joules per coulomb, the voltage, times the coulomb per second gives me joules per second, gives me the power that's coming in. The power that's leaving my system is coming out actually through those two different light bulbs that I have, where each light bulb here, right, I've got the two light bulbs, R1 and R2, each have a current I flowing through them. It seems that I actually know the current I that's flowing down through them, so I think I'm going to prefer the current form of the power through each of them. The formula for the power through them is this nice relationship I squared times R. So the total power out then is going to be I squared times R1. That's for the first bulb, plus I squared times R2. And the question is, are these things going to be equal? Well, I think we can see how we would want to check this. We're going to need to do some mathematical simplification on this side of the equation. The first thing that's really begging to happen is to gather R1 and R2 together. So this would be I, right, squared times R1 plus R2. Interesting. See, the next mathematical thing is I'm hoping to prove that it's the EMF times I, and it seems like I can factor out an I, so let's factor out I as my next step. So does that going to equal then I times R1 plus R2, and I've factored out that extra I. And now I'm feeling very excited because look at this thing. What is this? Look, I times R1 plus R2. That is something I think we know. If we go all the way back up to the top, here our initial equation that describes the behavior of the circuit, if I take I and multiply it by R1 plus R2, I guaranteed I get back the EMF of my battery. So when I have I times that here, I can simply now replace this combination with the EMF. And look at that. This side of the equation does actually mathematically match this side of the equation. Every last drop of power that I'm putting into my system is exactly what's coming back out of the system as light there in those batteries. So I'm very excited to see this fundamental rule of physics working. And so for this, we always like to give the happy professor symbol because with energy conserved, we know we've actually been properly here, accounting for our energy, and so there we go for that particular analysis.